we want to look at what we call eigenvalues and eigenvector under matrix. From what we know, this is the representation of matrix. Let's say M equals to A, B, C, D, and N is equals to A, B, C, D, E, F, G, H, I, right? From here, M is what? What type of matrix is M? This is a 2 by 2 matrix. Then N is what? 3 by 3 matrix. Now, this matrix as it is like this. Let's say we are given a question under matrix in this format. You can find the eigenvalues of this matrix and the eigenvectors of this matrix. Likewise, for 3 by 3 matrix. So what we are saying is that we want to look at the concept behind eigenvalues and eigenvector of a matrix. Now, by definition, what is eigenvalue and what is eigenvector? So both of them they are similar. There is a similarity between them. It's just that eigenvalues, as the name implies, eigenvalues is a scalar, while eigenvector they are referred to as vector. Now, by definition, eigenvalues, an eigenvalue is the scalar value that represents how much eigenvector gets stretched or shrunk by the linear transformation. That's for eigenvalues. Now, what about eigenvector? By definition, it is a special vector. It is a special vector. It is a special vector that, when transformed by a linear transformation, it only changes in magnitude. It only changes in magnitude. It also gets stretched or shrunk, but not in direction. We are saying that eigenvector, they are special vector, right? What happens to them? They get stretched and shrunk also, but it only changes in what? Magnitude, but not direction. Are you getting me? So that's the difference between eigenvalue and eigenvector by definition. All right. There are a lot of theoretical explanation on eigenvalue and eigenvector, but we are interested in computing the value of a particular matrix. Let's say you are given this matrix. What is the eigenvalue of this matrix, and what is the eigenvector of this matrix? Are you getting me? Likewise, this. Let's say you are given this matrix. What is the eigenvalue and what is the eigenvector? That's what we want to achieve today. We've defined what eigenvalue means, and we've defined what eigenvectors means, right? Now, mathematically, there's this relationship between eigenvalue, eigenvector, and a given matrix itself. That is, this given matrix is what? A. You are giving the given matrix A. Eigenvector is represented as V, and eigenvalue is represented as lambda. Meaning there's a relationship between these three parameters, and this is the relationship. AV is equals to lambda V. Call this equation 1, where A is the given matrix, lambda is the eigenvalue, then V is the eigenvector. Alright, with this, from equation 1, we can have something. From equation 1, we can derive this. This is the left hand side, and this is the what? Right hand side. Let's bring this right hand side to the left hand side. Equation 1 becomes what? AB minus lambda V equals 0. Observe, V is common, factorize. That is, A negative lambda all into bracket V is equals to 0. Call this equation 2. Now, what this means is that you'll be given a matrix, which is this here, A. Then that matrix, you subtract your eigenvalue from it. Recall, we said this lambda is what we call eigenvalue, and they are scalars. They are what? Scalars. That is, let me use this to explain. From here, let's compute A minus lambda. Let's compute this. A minus lambda using the information we have. This is A, right? And this is lambda. Lambda means scalar, meaning lambda can be 1, it can be 2, it can be 3. But in this case, we have A, which is what? A, B, C, D, E, F, G, H, and what? I. This is the matrix for A, right? This is a 3 by 3 matrix. Then this 3 by 3 matrix, it is subtracting your what? Your lambda. What is lambda? Lambda means what? Scalar, eigenvalue. Now my question is, in matrix, with the knowledge of matrix, is it possible to subtract something of this nature? Why? Because before you can subtract, what you are subtracting for must be a 3 by 3 matrix. Are you getting me? We said, is it possible to subtract something of this nature? No. Why? Because you can only subtract a 3 by 3 matrix from a 3 by 3 matrix. What if your A is given to be 2 by 2 matrix? They are saying that, what if A is given to be AB, CD, subtracted from this? Is it possible to have this in matrix? We should subtract this from this. No. Meaning that this equation 2, you can rewrite it with something else. So what we are saying in essence is that this equation 2 can be written as A negative lambda I equals 0. This is what? Equation 3. So given any question under eigenvalue and eigenvector, this should be your first task. You must record this equation 3. This is the relation that I am going to use. But from here, what hurts about this is that I is what we call the identity matrix. Identity matrix for a 2 by 2 matrix. Don't forget, diagonally, you have what? 1. Then fill up your matrix. The entry 0. Similarly, for a 3 by 3 matrix, diagonally, you have what? 1, 0, 0, 0, 0, 0, 0. So what this means is that your lambda, if it is a 2 by 2 matrix, call this A, call this B, or call this scene 1, call this scene 2. For scene 1, since it is a what? 2 by 2 matrix, it means your lambda will be multiplied by the identity matrix, right? And the question is why? By the time you multiply this lambda with the identity matrix, you will be able to subtract this matrix. Are you getting me? Yes. Likewise, if it is a 3 by 3 matrix, meaning scene 2, by the time you multiply this lambda by this identity matrix of a 3 by 3 matrix, you'll be able to subtract. Now let's use this to explain the concept. Meaning from scene 2, I have that A, B, C, D, E, F, G, H, I, negative lambda, all into brackets. What is the identity matrix of a 3 by 3 matrix? 1, 0, 0, 0, 1, 0, 0, 0, 1. Open up your bracket, meaning this lambda, lambda is what? Eigenvalue, scalar. And scalar can be 2, 1, 3, etc. So let's say you are using lambda direct here. You are using the value of lambda directly. By the time you open up your bracket, what do you have? A, B, C, D, E, F, G, H, I, negative lambda, 0, 0. Now, what led us to this is from scene 2. Now, from scene 2, the question is it possible to subtract something of this nature? No. Check this guy here. Is it possible to subtract? Why? Because we now have a 3 by 3 matrix here and a 3 by 3 matrix here. So what we are saying in essence is that your first task, the given matrix, write it out. Right? Yes. Then your eigenvalue, which is represented as lambda, multiplied by the unit vector of that matrix. If it is a 3 by 3 matrix, this becomes the unit vector. If it is a 2 by 2 matrix, this becomes the what? Unit vector. And that's the idea. So this is equation 3. So what this means is that whenever you are given a question under eigenvalue and eigenvector, we call your equation 3. Are we clear? So that's the concept behind eigenvalue and eigenvector. Now let's take down our first example to see how it works. Which one is that? Oh, that's true. We have V here. Alright, let's take down our first example. Find the eigenvalue and eigenvector. Find the eigenvalue and eigenvector of the given matrix. This is the given matrix. A is equals to 4, 3, 1, 2. This is your given matrix. The question says that find the eigenvalues and eigenvector. Solution. Your first step. What's your first step? I told you that whenever you are given a question, first thing first, identify. Is this a 2 by 2 matrix or a 3 by 3 matrix? 2 by 2 matrix. The identity matrix becomes what? I is equals to 1, 0, 0, 1. Right? Now, having identified this, your next step is what? Come back to equation 3. What do you say? Come back to equation 3. Is equation 3 you are going to make use of. By equation 3, it means you need A, and this is A. You need the product of lambda times the identity matrix. Right? Now, let's compute. What was lambda times identity matrix? It implies what? Lambda, what's the identity matrix? This guy here. 1, 0, 1, 0, 0, 1. Let's get the value. This is what? Lambda, 0, 0, and lambda. Are you with me? Now let's work with equation 3. Since that's what we are using. By equation 3, it means the given matrix, which is this, 4, 1, 3, 2, subtracted from lambda, 0, 0, lambda. For now, let's work with this. When you are working with this, what it means is that you want to get eigenvalues. Eigenvalues. You know, we are not complete here. This equation, we've not considered it all. What haven't we included here? V, exactly. And what's V? Eigenvector. Meaning, you must know your eigenvalue before you know your what? Eigenvector. Now, we want to work out our eigenvalue. Let's consider this first. That is, I'm considering what? A negative lambda I. If I know the value of this, after calculating the eigenvalue, I'll come back to this equation 3 to use my V, which is my eigenvector. So in that case, V becomes the unknown. But let's see how it works. Now let's solve. Subtract. What do you have? Apply the same idea here. The way we subtracted, apply it here. You know, from here, by the time you subtract this, your matrix, this is your row, this is your column. Row 1, column 1, row 1. What do you have? A. Column 1, row 1, column 1. What do you have? Lambda. Or better still, do comparison. By the time you do comparison, you have A here. What do you have here? Lambda. Meaning A minus lambda. Same comparison. This minus this. What do you have? B. B minus 0 is what? B. C minus 0 is what? C. What do you have here? D. This is what? E minus lambda. F. G. H minus. Okay, just H, right? Then this is what? I minus lambda. So this is the idea that I'm going to apply here. Just that in any given matrix, without solving A minus lambda I multiplied by the identity matrix, just that diagonally, all the value will be subtracted from lambda. Then you repeat the initial value there. Yeah, what's your question?
Is it in a multiplication of use row to column, row to column, like?
Oh, that's determinant.
Yeah, that one is
Find determinant. But for now, just do comparison. Just do comparison. Now let's solve this guy here. Moving on. What do we have? We then have that 4 negative lambda, this minus this. becomes this, right?
Yes.
This minus this, what do you have? Please call the values for me. What do you have? Okay. The next one is what? 3. The next one is what?
2 minus lambda.
2 minus lambda. From here, what do you just do? You solve a minus lambda I. And what your task here is, you want to get the value. You want to solve for eigenvalues. Let me put it that way. You doing this, what it means is that you want to solve for what? Eigenvalues. By the time you know eigenvalue, you'll be able to get eigenvector. Each eigenvalue that you have has their corresponding eigenvectors. Are you getting it? Each eigenvalue, they have their corresponding eigenvector. In other words, you can say that eigenvector depend on eigenvalues. You must know eigenvalue before eigenvector. Now, from here, you are familiar with this. Recall, when you have A, B, C, D, let's call this A. The determinant, meaning delta A, is equals to what? A times D minus C times B, right? Relate this with this. Is it the same?
Yes.
This matrix relates it to this.
Yes.
What we applied here, the way we found our determinant here, can we also do that there?
Yes.
The answer is yes. Now let's solve. Applying this concept, it becomes what? All into bracket 4 minus lambda, this times this, right? All into bracket 2 minus lambda, negative 3 times 1. Close your bracket. Open up. This times this, what do you have?
6.
This is what? 8. This times this, negative 4 lambda, negative 2 lambda, positive lambda square, minus 3. Any questions so far? This times this is what we are doing. You distribute 4 all into bracket 2 minus lambda, negative lambda all into bracket 2 minus lambda. 4 times this, what do you have? 8. 4 times this, negative lambda. This times this, negative lambda. This times this, positive lambda square. And that's what we got here. Any question? Now moving on.
Minus lambda and minus lambda.
And now negative times negative, positive, lambda times lambda, lambda square. From here, meaning 8 negative 6 lambda plus lambda square negative 3, right? Any question? Negative 3. That is lambda square negative 6 lambda plus 8 minus 3. You then have lambda square negative lambda plus 5. Now go back to equation 3. Equation 3 says that A minus lambda I V equals 0. Meaning, it is from we got this using equation 3. That is, this expression you can equate it to 0. Since I'm applying equation 3, you can relate, this expression that we got from equation 3, you can equate it to 0. And why? If we check equation 3, it was equated to 0. You get? Now, equating this to 0, what does it mean? Okay, let's do it this way. Why performing all these things? What's my interest? What do I want to find? Engine value, exactly. I want to find engine value. What do we say about engine value by definition? We said engine values are what? Scalars. And we said engine value is denoted with what? Lambda. Now check this equation here. This equation, you can relate it to quadratic equation. And by quadratic equation, you can surely find the root of quadratic equation. Because let's say you have ax squared plus bx plus c equals 0. From here, you can get what? X1 and what? X2. But in this case, instead of x, what are they using? Lambda. Meaning from this equation, I can get what? Lambda 1. I can get lambda 1 and what? Lambda 2. And initially we said lambda is representing what? engine value, meaning any value I get for lambda becomes my engine value of this matrix, and that's it. Any question? No, your task now is to find the root of this equation by factorization. By factorization. Now let's factorize. They go out sleep. Yes, I need to try. I want slow. Mom, this thing will be place well. I'm beginning on the able check this thing. What about on green light? Okay, now from here, let's solve this equation. When you want to solve, meaning find the root of the equation, any value we get becomes what? Engine value. Now let's solve. X, we have lambda square negative 6 lambda plus 5 equals 0. Factorize. Factorize. Let's factorize. By factorization, it means any number that by the time we multiply, we get the product of this and this, then by the time we add, we get this. And that number is what?
Minus 5.
Let's think. What will be that number? What's that number? Minus 5 and minus 1. That's correct. Minus 5 lambda and what? Minus lambda. Now let's perform the multiplication. Minus 5 lambda and minus 5 lambda times minus lambda. What do we have? Positive lambda square. Then negative 5 lambda plus open bracket minus lambda. That is negative 5 lambda minus lambda. What do you have? Negative 6 lambda. Observe, these two numbers, by the time you sum it up, you get what is in the middle. By the time you multiply, you get the product of this and this. And that's the concept behind factorization. Okay? Then lambda square negative 5 lambda negative lambda plus 5 equals 0. That is, from here, you have lambda all into brackets lambda negative 5 plus lambda minus 5 equals 0. You have an invisible one here. There's an invisible one here. Yes.
It's minus 1. Minus 1. It's minus 1.
Yeah, that's correct. Negative 1. Because by the time you open up this bracket, by the time you distribute this over, you get the same equation. By the time you distribute this, what do you have? You get the same equation. You understand? So from here, since these two are common, bring these two guys together. Lambda minus 1, open bracket, lambda minus 5 is equals to 0. Now separate. Lambda minus 1 is equals to 0. Exactly. Or lambda minus 5 is equals to 0. That is, make lambda the solid of the formula. Therefore, lambda is equals to 1 or 5. Any questions so far? From here, lambda is equals to 1. From here, lambda is equals to 5. So what you are saying is that, okay, lambda is equals to 1 or lambda is equals to 5. Or better still, say lambda 1 and lambda 2. Meaning lambda 1, you know, this is the engine value of this matrix, of the matrix we have earlier. This is the engine value. This is also the engine value. What it means now is that this engine value has its corresponding engine vector. This engine value has what? Its corresponding engine vector. Likewise, this guy here. There's a corresponding engine vector for this engine value. You now estimate the engine vector using that same equation 3. Can you see how equation 3 works? The first thing using equation 3 is what? Solve for engine value. Number 2, using that same equation 3, solve for engine vector. And that's it. Now let's go back to equation 3. Let's solve for our engine vector. Now recall. What was our equation 3? Our equation 3 says that A negative lambda I, then what do you have here? B equals 0. You know, before we got this equation, we have this initial equation, which is what? A V equals to lambda V. So it's either you use this or you use this to compute your engine vector. Let's use this, which is from equation 3. It is from this equation 1 we derive equation 3. Now this is equation 3. Earlier we derived equation 3 from 1, meaning when you want to get your engine vector, it's either you use equation 1 or equation 3 to solve for engine vector. So I'm going to use the both of them. I'll use 1 and 3. Now using 1 first, what you are going to do here, since you are calculating engine vector, now ask, this matrix, is it a 2 by 2 matrix or a 3 by 3 matrix? 2 by 2 matrix. So you get two value of engine vector for a particular engine value.
So if it's 3 by 3 matrix,
you get 3. You get 3.
You get 3 engine values.
Yeah. You get, if it's a 3 by 3 matrix, you get 3 engine vectors.
Or 2 values. Wait. 2 is 3 by 3 matrix. You get 3.
This is how it works. This is how it works. For 3 by 3 matrix, a engine value we give 3 engine vector. Engine values, a particular engine value we give 3 engine vector values. Just one we give 3. The second one too we give 3. The third one too we give 3. Are you getting it? But let's use this principle to understand how engine vectors work. Now from here, what do we solve? When we've computed the value of a negative lambda I, right? So what is it? What do you have? Like, what was our matrix when we solved for this guy? What was the matrix we got? Exactly. I have, okay, before then, you know that you want to get V now. Why is it V? Because V is representing engine vector. Since it is a 2 by 2 matrix, you will now say that let your V to be a column matrix of x1 and x2. Since it is a what? 2 by 2 matrix. In a case whereby you have 3 by 3 matrix, it becomes V is equals to x1, x2, x3. This guy here is a column matrix. So you are representing your engine vector with a column matrix in this manner. Likewise, this works for 2 by 2, this works for 3 by 3. You understand the concept now? So back to the question. Meaning anywhere I see V, what will I substitute? This column matrix, because I've represented it. You just say let your engine vector for 2 by 2 matrix to be this column matrix, which is x1, x2. That is, anywhere I see V, it becomes this guy here. Now let's substitute. Earlier, we've computed the value, the matrix of a negative lambda I. And what was it? This man here. Right? So you are repeating that 4 minus lambda 3. This is 3. 1. 2 minus lambda. Now, in place of V, what will you have? A column matrix representing your engine vector. And that will be what? x1, x2 equals 0, 2. Since you get two values, represent your 0 like this. If it is a 3 by 3 matrix, you have 3, 0. Are you getting the logic? But now, you have two values of engine vector. When the first one is when your engine, you have two values of engine value. You got two engine values, right? The first one is when your engine value is equals to 1. Right? The second one is when your engine value is equals to 5. Now let's work for the first one. Right? When lambda, which is your engine value, is equals to 1. Meaning from this matrix formation, anywhere you see lambda, what will you substitute? 1. Are you getting it? So from here, 4 minus 1, what do you have? 3. This becomes 3. This is what? 1. 2 minus 1, what do you have? 1. This remains the same. x1, x2 equals to 0, 0. Now you can relate this to your product matrix. You can multiply something of this nature. This times this, what do you have? 3x1. This times this plus x2 equals 0. This times this, 3x1. This times this plus x2 equals 0. Call this equation 1. Call this equation 2. Either equation 1 or both of them, they are the same. Equation 1 and equation 2, they are the same. Yeah, what's the question?
You said this can divide with use 1.
Yeah. You know, we got to one. We got to.
Choose 1. I'll go to use 2.
We will use 1. We use 2.
What if the answer is?
In this case,
That one, I said the two equations. We always
it doesn't mean it will work hand in hand. It will work hand in hand.
we always try.
It will tally exactly. Okay, now I remember what I wanted to say before. Now, how it works is that this particular eigenvalue now, you have two, you know, it is a 2 by 2 matrix. This particular eigenvalue, you have 2 eigenvectors. This one too. This is this is also eigenvalue. This eigenvalue, you also have 2 eigenvectors. Now, for this guy here now, he said, well, this is the eigenvalue, and the value of the number for the eigenvalue is what? 1. And we've substituted 1 anywhere we see lambda. Then that's how we got this. Then from here, perform your normal matrix, multiply. This time this, this time this. Are you getting it? Then this is what? Equation 1 and equation 2. Then you observe that equation 1 is the same thing as what? Equation 2. Now from equation 1, you know, equation 1 is still the same thing as equation 2, so it doesn't mean it's either you use equation 1 or you use equation 2. Now, from equation 1, you want to know both value of x1. You know, earlier you represented your eigenvector to be what? X1, x2. So you are interested in knowing the value of x1 and the value of what? X2. Using this equation. Now, from equation 1, you have that 3x1 plus x2 equals 0. That is, this guy can go to the other side. It becomes 3x1 is equals to negative x2. From here, it implies that x2 is equals to negative 3x1. From equation 1 here, this is it, right? Then this x2 going to the other side turns to negative. From here, make x to the result of the formula. That is s2, you know, minus will go to the other side. It's just like you dividing both sides. It's negative 1. So this cancels this. Then you have s2 is equals to negative 3x1. Any question on that? Now from here, how are you going to interpret? You know, you want to get x1, x2. How do you interpret this guy here? What it means is that what if your s2 is 1? Sorry, if your x1 is 1, s2 will be what? Negative 3. Okay, s2 is negative 3 times x1. What did I say? I said s2 is negative 3 times x1. Based on what you get here. That meaning if if x1, our absorption might be different. Now, let me say I'm using x equals to 1, and you are using x equals to k. You are using x equals to k. I want to interpret this equation. Now, when x is 1, s2 will be what? It will be negative 3 times of x1. Now, if x1 is 1, then s2 will be what? Minus 3. And how do you get minus 3? Negative 3 multiplied by x1. Are you with me? This is the first assumption. When x is k, when x1 is k, x2 becomes what? Negative 3k. Are you getting the logic? So what this equation means in general is that any value of your x1 multiplied by 3 multiplied by negative 3, it will give you what? S2. Any value you assume for your x1.
Even for 3 by 3 matrix.
Yeah, even for 3 by 3 matrix. If you have something like this, in some question, you get the value of x1 directly and you get the value of x2 directly. Meaning, from question, by the time you solve, your x1 might be 0 and your x2 might be 1. It doesn't mean anything. But in a case like this, you know, this is where you are coming back to. This vector, you must write it in this column matrix. You must be precise. You must know the exact value of x and the exact value of y, of s2. But here, we didn't get x1, neither s2. So you must interpret. So I'm now doing this assumption that if my x is if x1 is 1, then x2 will be what? Negative 3 times x1. So this is the first case here. Case 1, case 2. Are you getting me? So at the end, writing this your engine vector as 1 and negative 3, or k and negative 3k. Are we correct? You are correct. The only difference is that here your x1 is what? 1, but here your x1 is what? K. But they are defining the same things. It is saying that when x1 is 1, s2 is negative 3 times 1, and that's it. Now, but what you just did here, you only got when engine value is 1, your engine vector, these are the value. But now, when engine value is 5, what will be the engine vector? Same idea, you solve the same process, nothing is changing. The same way you solve for the engine vectors of 1, that's the same way you solve for engine vectors of 5. And this idea, that's what you are going to use to solve a 3 by 3 matrix.
This equation really down. How you do it?
And now this time this is this normal matrix. This row times column. This time this is this. 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 You are just performing your normal matrix. This time this will give you this. This time this will give you this. So that's it. Now let's quickly solve for let's find the value of engine vector when engine value is 5. You get the point. Right. For the given matrix, what's the given matrix? Recall, what's the given matrix again? 4 minus lambda 1. 4 minus lambda 3 No. I mean the initial matrix. 4 3.
Okay, the initial matrix is
4 3 1 2.
1 2. Okay, this guy here now, this is the given matrix. Now what are the engine values? Engine values are what? The first engine value we got 1. And what are the corresponding engine vectors?
4 minus lambda.
The corresponding engine vector 1 and minus 3. Now when your engine value is what? When your engine value is 5. Now let's find the corresponding engine vector.
Value 2.
Okay, this is engine value 2. Now let's find the corresponding engine vector when this engine value is 5. Go back to what? Equation 3. It's either use this equation 3 or equation 1. For the first one, I use equation 3 to solve.
No, use equation 1.
For the first one, I use equation 3 to solve. For the sake of time, this 5 now, I'm going to use equation 2 to solve. Equation 1 to solve. So you can play around both 1 and 3. You get? Let's solve for, I want to solve for engine value now. When your engine value, meaning x2 is 5, you are looking for the engine vector. Denote it as s1 and s2 also. Now from here, using equation 1, what's A? What's A? What's A? This is
4
A.
minus lambda.
4
Minus.
No, you are using equation 1. It's either equation 1 or equation 3. It was equation 3 that we used to solve for the first one. Now I want you to see how it works too for equation 1. I would have solved that same first one using equation 1, but for the sake of time, we don't have much time. So I'll just use this one directly to solve for the second one. So you see how it works. So now for this one now, just that it's just as if you've gotten the value already. You are now doing substitution. This is equation 1. A, what's your A? What do you define A at with? A matrix, which is this 4 1 3 3 2. What's your B? Engine vector. Yeah, engine vector.
x1
x1 x2 x1 x2 equals to what? Lambda
5.
Lambda. In this case, what's your lambda? 5
x1
x1 x2. Exactly. x1 x2. Let's solve. Then you have 4, 1, 3, 2, x1, x2, open up. 5x1, 5x2. Now multiply these two matrices, meaning 4 times this, 4x1, this times this, plus x2 equated to what? 5x1. 3 times this, 3x1, this times this, plus 2x2 equated to what? 5x2. This is equation 1 and this is equation 2. Either equation 1 or equation 2. Both of them will give you the same value you get for x. Using equation 1, you have the value of x1 and s2. The same value you get for x1 and s2 using equation 1, that will still be the same value you get using equation 2. Now let's use equation 1. It's more of like substitution method. Now let's use equation 2 here. No, equation 1. From equation 1, we have that you observe that x1 you can collect like 10, right? Meaning, let's make s2 the surrogate of the formula. s2 is equals to 5x1. This one will come to the other side. Negative 4x1. Then it implies, or you say therefore, x2 is equals to 5x1 minus this. What do you have? x1. Using what? Equation 1. Now let's use equation 2. Make this guy the surrogate of the formula. 3x1 is equals to 5x1 negative 2x1, right? So what am I saying? This is 3x1 equals to 5s2 minus 2s2. Then this becomes 3x1 equals to what? 3x2. Then this cancels this. What do you have? x1 equals to s2. From equation 1 we got this. From equation 2 we got this. Is there any difference? No. So what it means is that whenever you have these two equations, the value of x1 and s2 that this first equation will give you, that's the same value that equation 2 also give you. Now from here, how do you interpret this guy? s1 is equals to s2. Meaning if x1 is 1, s2 is what? 1. If x1 is p, s2 is what? P. Now it depends on you. What should we conclude it as? Is it 1?
Yes.
If s1 is 2, meaning s2 is also 2. But yeah, let's use 1. So let's say that let x1 is equals to 1. Therefore, s2 is equals to what? 1. Now come back to this place. For the engine value vector of 5, for the engine value which is equals to 5, engine vector becomes what? 1, 1. And that's it. So this is the concept behind engine vector and engine value of a matrix. But what we did here, this is for what? 2 by 2 matrix. The same way you solve for 2 by 2 matrix, nothing is changing. You solve for what? 3 by 3 matrix. But in that case, where you get it complicated is when you want to solve the root of the equation. When you want to solve the root of the equation, it was easier for us here because we are familiar with this type of equation. This is a quadratic equation. In a case whereby you have polynomial equation, by polynomial equation, I mean the highest degree is starting from 3 and above. Are you getting me? This is what I'm saying. Let's say for polynomial equation, we have s cubed plus 2x squared plus 11x negative 6 equals 0. You can't compare this equation with the one we solved. That one we can factorize directly. But this one is either you have to find the root of this equation too. But how do we find it? Now, from here, you now recall your polynomial. From here, there's one called remainder or remainder rather. Meaning you'll be doing trial and error. If x is equals to 1, by the time you substitute the value of if lambda is equals to 1 here, by the time you input 1 here, if 1 gives you 0, what does it mean? It means x equals to 1 is the root of this equation. And by x equals to 1, how do you get x equals to 1? It is from x minus 1 equals 0. Are you getting me? It is from what? It is It is lambda, it is from lambda minus 1 equals 0. Meaning lambda minus 1 is a root of this equation. It will be the root of this equation only if by the time you substitute x to be 1, you get 0. And this is taking us back to polynomial. You know, from polynomial, we said a given polynomial f of x is still the same thing as the quotient plus the quotient times divisor plus remainder. But we don't need this. This is what I need for now. So what you are saying is that this guy here, if you are getting 0, when you substitute x equals to 1, meaning x minus 1 is a factor of this equation. Now, to now get the other factor, we already know that x minus 1 is a factor of this equation. Now, to get the other factor, you now use long division rule, meaning x minus 1 divided by lambda cube plus 2 lambda square plus 11 lambda negative 6. By the time you solve this long division, you get a quadratic equation that you'll be able to factorize and get the other roots, right? Now, but there's a trick you can use. In exam, you can quickly input any given polynomial into your calculator and know those roots. And from there, you just play with it. In the next video, we are going to compute the Eigenvalue and Eigenvector of a 3x3 matrix to see how it works. So whenever you encounter this type of equation, which is a polynomial of degree 3, you know how to solve it. Alright, if you find this video interesting, do well to give it a thumbs up and encourage us, subscribe, comment, and share your thoughts.